Hi there. Judging from my own family, you probably have a ton of USB charge cables lying around. Some came with expensive stuff like tablets and phones, and other came with all kinds of cheap gadgets, but it's almost impossible to tell the cable quality from the outside. Soon the cables all get mixed up, and as long as they have the right connector, we use whatever cable is handy. In my experience, the USB cables are now almost exclusively used for charging, since most of the data connections use much more convenient Wi-Fi. So I thought it would be useful to investigate if there's an easy way to test the charge performance of a USB cable using only a USB power source, a USB tester, and some LED lights as load to make this an easy test you can repeat yourself at home. Why is this important? Well, consider the usual scenario where you charge a device like a phone from a charger or a power bank. If your cable is really bad and has a total internal resistance of say 1 ohm and you are charging at 1 amp, then from the 5 volts delivered by your charger, only 4 make it to the phone. That's 20% loss, or 1 watt, in this case, which just disappears as heat in the cable. This also means you are waiting 20% longer for your phone to be fully charged. Now we are talking really low resistances here. 1 ohm for a cable of say 1 meter is already a lot. So measuring the resistance directly with a multimeter is tricky. Here is a USB cable with a micro USB plug on one side and the standard USB-A connector on the other. For a start, it's not easy to probe the cable with a multimeter. I have used these 2 breakout boards, which you can get on eBay, and shortened the micro USB end to measure the total resistance of the plus wire going from the USB-A to the micro USB connector and the resistance of the negative return wire at the same time. This is easier to measure more accurately than just measuring the resistance of either the positive or negative lead and then doubling the value. In any case, we need to null the resistance of the measurement leads first by selecting relative mode. About 0.7 ohm, which is rather high. Cheaper multimeters, such as this one, don't have a rel or null function. In this case, you must take note of the value with the lead shortened and then subtract it from the reading when measuring the cable resistance. So with lead shortened, the meter reads about 0.5 ohms. And the cable resistance is read as 1.2 ohm. Subtracting 0.5 from 1.2 means the actual resistance is around 0.7 ohm, similar to what the BM235 found. So this method works, but you need a multimeter and some way of accessing USB connectors on both sides, which isn't easy unless you have these breakout boards. Luckily, there's an easier way if you have a USB tester. The UM34C is such a USB tester, and it even has a built-in function to measure cable resistance. While the voltage and current measurement functions of the UM34C are quite good, the implementation of the cable resistance function is seriously flawed, as I pointed out in my review of the UM34C, which I link into the description of this video if you haven't seen it. So we shall not be using that function. I also want to bring in my slightly older USB tester, the UNI-T UT658, which has not nearly as many functions as the UM34C, but does basic voltage and current measuring, however at less resolution and accuracy. In case you are interested in my review of the UT658, I put a link to that video in the description as well. The usual way to measure cable resistance with a USB tester and a load is the 2-step process described here. First, measure the voltage and current directly connected to the power source. Then, in step 2, put the cable in between and measure again. The cable resistance is then easily calculated based on the voltage difference. The critical point here is that the source voltage and the load current must remain the same for both steps. The first condition is usually the case with any half-decent USB charger or power bank if your load current stays reasonably within its maximum rating. The real problem is what you use as a load. Ideally, you would have an electronic load which keeps the current constant, in which case everything works as shown here. Most people won't have one, and every other type of load will cause the current to change when the voltage at the load changes, and that it will because of the cable resistance. A commonly available load is a USB LED light. Let's look at some USB lights to be used as loads. The first one has a 15 ohm current limiting resistor and 3 LEDs in parallel. At 5 volts it draws around 126 milliamps. They are very cheap on eBay as they are just basic circuit boards, but they get hot and it's very easy to burn your fingers. The same principle but enclosed and therefore slightly safer to touch. This one has 4 20 ohm resistors in parallel, so 5 ohms, feeding 8 LEDs in parallel. It draws around 378 milliamps. The last one is one of those flexible light sticks. They come in packs of 5 on eBay. You can't see what's inside other than there are 6 LEDs. It draws around 211 milliamps. For best accuracy, we shall use the one that draws the most current within the capacity of the power bank, which would be the 8 LED enclosed light. I have measured the current drawn by each of these in the crucial range from 4 to 5 volts, and as you see, the current changes depending on the voltage. Moreover, it may look as if the change is linear, but it isn't. At 5 volts, the 8 LED enclosed light, shown in yellow here, draws a current equivalent to a 13 ohm resistor. But if you plot the linear graph of a 13 ohm resistor onto the chart, as I have done here with a dashed line, you see that the 8 LED light increasingly deviates from it. At 4 volts it behaves like a 19 ohm resistor. This is of course because the nonlinear behavior of diodes and all the other LED-based lights show the same behavior. This means LED lights are unsuitable as loads for the cable-resistant measurement procedure shown earlier. But as I explained earlier, any decent USB power supply or power bank will be able to maintain its output voltage reasonably constant if the load current drops slightly in step 2 because of the reduced voltage reaching the LEDs due to the cable loss. This means we can amend the procedure as you see here. In step 1, you only need to read the voltage and ignore the current reading. Moreover, if you have multiple cables, you only need to do step 1 once, provided your power supply, like a USB power bank, doesn't run out of charge during the process. Let's try it with the UM34C. First, the direct connection to the power bank. 5 volts. Now inserting the cable. With the UM34C this is particularly easy because it has a micro USB port. .74 volts and 0.339 amps. Okay, 5 volts from step 1 minus 4.74 equals 0.26 volts as a voltage drop. So divide that by 0.339 gives a resistance of about 0.77 ohm, which confirms the measurements by the multimeters earlier. Doing the same test with the UNI-T UT658. The voltage when connected directly reads 5.04. For inserting a cable, I use a micro USB to USB-A female to female adapter you can buy on eBay. .81 volts and 0.36 amps. So 5.04 from step 1 minus 4.81 gives a voltage drop of 0.23 divided by 0.36 is a resistance of 0.64 ohms, which is a bit on the low side. But given the UNI-T's limits in accuracy and resolution, the results is still reasonable. In any case, a UNI-T will still allow you to compare a range of cables and pick the best ones. I'm speeding up the measurements of a collection of micro USB cables. The procedure is always identical and only step 2 is needed. For good measure, I added a few USB-C cables, which is very easy because the UM34C has already a matching connector for it. For the UNI-T, I would need to find an adapter first. Here's a spreadsheet with the results. The measurements are in these columns. This is the voltage and after the cable, and this is the current, and this is the direct connect voltage. The resulting resistance is in column F, and here is the black cable that we have examined earlier. It's one of the worst cables in this list. I also added column G, normalizing the resistance to a cable of 1 meter length. This allows some judgment on the relative quality of the cable cores, in other words the thickness of the conductors against each other. Obviously more metal is more expensive, and so manufacturers try to cut corners and use the thinnest wires they think they can get away with. The winner of the best conductor is the white micro USB cable of 98 centimeters length, and the worst is the black cable that we started with. The black cable has 5 times the resistance of the white one, but you could not tell this from the outside. The rather long white USB-C cable, on the other hand, looks pretty bad in terms of its measured resistance. But since it's almost 2 meters long, the normalized resistance shows its cable core isn't nearly as badly made as the 3 black micro USB cables below. For practical use, you need to use column F and choose the cable with the lowest resistance that is long enough to do the job. All these cables here now are better choices than the winner of the best conductor award, and that is simply because they are shorter. It is clear that at least the last 3 cables here should not be used for charging at all. I'm not going to throw them away just yet, but mark them with yellow tape to avoid using them for anything but data transfers. On some of the others I wrote the resistance on the plug. And that's it. I hope you found this useful. Please leave comments or give a thumbs up, and don't forget to subscribe if you haven't done so already. Thanks for watching.